So this is an example of composite UML diagram. And so once again, the idea is that we can have a tree structure like this, right? So we can have basically the tree may look like this and could have any level of complexity, but just to try to use an example like this. Okay, so these are terminal nodes right here that terminate branches, and these are branch nodes like this, right? So these are branches. Now typically we say that this is a parent and this is the child. So typically this is how you describe parts from which you construct your tree, right? And so composite here is an example of the branch node, right? So composite is this. Basically, composite says I am a composition of other parts in this structure, and the leaf or terminal node is this example right here, right? So we have essentially the node that has no children. It's the final node in this specific branch. And so the idea of construction here is to have an interface and completely rely on the interface of a component from which we can build. So there could be all sorts of operations related to computations and processing data inside all of these nodes, and we call them generically operation. But there are also operations to construct the tree, like add and remove. Okay, so we can construct the node and add another branch to it. And there could be also trees with not just like binary branches, but there could be other more complicated trees like this as well, that you can have multiple children, not just one or two, but more than two. And also you can obviously say get child and specify which one by index or right and left if it's a binary tree. And an idea here is that both terminal nodes and composites or branches, the nodes that represent branches, expose and implement the same interface. So each component declares its interface for objects in composition. What it means is that all of this, every connection in the tree that we have, that of course we link the nodes by these connections, they all are of type of reference to this type of interface, right? So each connection here is basically having a reference of this type in the parent, pointing to the child. So if necessary, component implements default behavior common to all classes, and that's just pretty much the choice here, right? So we need to essentially any possible operation that we need here and here has to be present in this interface. Otherwise, the idea doesn't stand. So the leaf represents the terminal objects, the composite represents branches, and composite also implements method to manipulate children. So this is add and remove. So now back to the UML diagram, we indicate here that pretty much this is our interface. The leaf, of course, implements the operation. Add and remove and get child are all implemented at the base class level. Now, in the composite case, it also stores collection in its data attributes, collection of children. And again, it's using this type of child. So when the nodes are created, we create specific type of nodes, but when we put them in the tree, we only store references of the interface or base class type in the tree. All right, so this is an idea of composite, and this is a class diagram that would allow us to create a tree. So there is a C++ sample for you to take a look at using the using C++ programming language, but just a quick set of sort of like advantages and disadvantages using composite design pattern. Composite, so first sort of like set of benefits. The clients use component class interface to interact with objects in the composite structure. So that top level base class for both leaf and composite. If call is made to a leaf, the request handled directly. If it's a composite, like with our example with multiplication and addition operations, it forwards its request to child components to complete to complete their own work, and eventually composite returns its own value back to the caller. So the disadvantages here is that once the tree structure is defined, the composite design makes the tree overly general. General means there are very little restrictions or constraints on or rules that we can impose. It's really just the entire code that handles this tree, or a combination of terminal and branch nodes, has to cannot be restrained using any other facilities from the tool set of the programming language itself. The entire set of restrictions that we prefer to have will be on the shoulder of the programmer. So it's just hard to enforce a strongly typed, approach to managing this tree. But perhaps that's still a trade-off, because the benefit is that we can construct in the unrestricted way, we can construct complicated trees out of these individual components. So to enforce any constraints, the program must rely on runtime checks and cannot use the type system of the programming language. So essentially, what this idea, how this constraint can be demonstrated, talking about, for example, again about arithmetic expressions. So we could try something like this. We could try to specify an invalid expression. For instance, we can say multiply, all right? So we can say multiply 5 plus 2, okay? So multiply is a binary operator, so it requires the left-hand side and the right-hand side. And so therefore it's a syntax error. You cannot compute expression like this because it's not using legal syntax. However, it's still possible to attempt to construct some sort of a tree, right? So we could construct a tree like this, like multiply right here, and we can specify basically 5 over here, and we can specify plus and 2, and so we can still try to construct something out of this. Some version. I'm just trying to get something quickly shown here. So essentially, we can still try to make a tree out of this structure. Okay, but at some point we need to be able to say, no, this is still not good. Although we constructed something with all of the components, we attempted to construct this tree structure, but it still is unusable. But this can happen only at runtime, right? So we cannot just kind of like enforce any of the rules at the time when we compile this program, because we cannot really rely on the type system of the programming language in this case, because it's just the tree structure is way too flexible. It allows to make structures even corresponding to illegal syntax versions of these input expressions. And so that's sort of like a disadvantage. It's just something that we need to be disciplined about, and that's okay. But it's just an idea behind this design pattern, that you need to be careful when testing your code and trying to verify all possible situations with respect to potential logical errors when constructing the tree, and be able to validate the structure of your tree as opposed to just always expect it to have a correct structure.